Welcome to the TB2J tutorial. In this video, we're going to learn how to calculate the Janoshinsky-Mollier interaction and anisotropic exchange parameter with TB2J. There are three steps for doing this. First, we need to generate three structures with the z-axis rotated to x, y, and z respectively. And we can do this with the script TB2J rotate.py. And then for each rotated structure, we do one non-collinear spin DFT calculation and run TB2J. In this step, use funny function or with CS star or OpenMX. So we can then use the corresponding script for the TB2J calculation. We will use the 2D material chromium iodide as an example. Let's first try to generate the rotated structures. Now, suppose we have the structure in a file, be it a zip file, or a VASP file, or XYZ file. We can use this command TB2J rotate.py to do the rotation. Let's see how to do that. So it takes the file name as the input, and we need to specify what kind of file it should generate. For example, the XYZ file or VASP file. But with this, please make sure that this format contains the full cell matrix. For example, in a zip file, this is not there. For example, let's have a look at this zip file. So you can see it has the A, B, C, alpha, beta, gamma, but it doesn't have the cell matrix. In that case, when we rotate, it will be always the same. So let's use other formats. And let's try T2J8 .xyz f type xyz. So then the three structures called items x.xyz and so on are generated. And we can have a loops x.xyz, and it has this cell parameter and the positions. You can check if the rotation is correctly done with your structures generated. Then for each structure, we need to do the DFT calculation, and we can make three directories here, for example, x, y, and z. And for example, in the z direction, we have already prepared the input files using the generated rotated structure. And we can have a look. And remember, we have to save the Hamiltonian and the overlap matrix, and we have to turn on the spin-orbit coupling to get the Janoshinsky-Mollier and the anisotropic exchange. Okay, so let's do the calculation. Now with the DFT calculation finished, we can run TB2J. This step is basically the same as in the collinear spin calculation. We could run cs*2j.py, and we specify the FDF file name, which is cs*z.fdf here. The elements, which is chromium, and the image. Okay, now we have the results in the TB2J results directory. You can have a look. In the exchange.out file, we can see that we have the cell parameter and the magnetic moment. Now, because it's a non-collinear, you have the x, y, z component of the spins. And then we have the exchange parameters. And here we have the isotropic exchange, the Janoshinsky-Mollier, and the anisotropic exchange. Note that in this calculation, some of the DMI and anisotropic exchange components are wrong because they are not physical in this perturbation. And we need to them in the other two calculations, and then in the end we can combine the results. That's why we need to do three calculations. And here we can have a look at the result. Indeed, you can see that here this anisotropic exchange is super large. That's because it's not meaningful. And we can then do the other two calculations in the same way. We do the TB2J calculation for the x direction, and the DFT calculation and TB2J calculation for the y direction. Now the three calculations are finished. We can use TB2J merge to combine the results into one. So with the three calculations done, now we can use the script TB2J merge to combine the three results into one. Let's see how to do that. We can use TB2 merge.py, the three directories, which are x, y, and z, and we have to specify the type of rotation we did. Actually, there are two kinds of rotation we can do. One is to rotate the structure, and the other is to rotate the spin. But as for now, some of the DFT code cannot rotate the spin, and the volatilization can be more difficult. So usually we choose the rotation of the structure. And we can see that we have a new TB2J results directory. Let's have a look. And we can see that we have the exchange, the DMI, the Januszynski interaction, and the anisotropic exchange. Now we can see that this number is much smaller and more reasonable. And we can also have an overview of the exchange parameters and DMI and so on. Let's have a look. So we could see that we have the first neighbor, second neighbor, third neighbor, and so on, the J. And we can see that the first neighbor Januszynski interaction is 0, but for the second neighbor it is non-zero. And for the anisotropic exchange, we have the first order, first neighbor, second neighbor, and third neighbor, and so on. Okay, so the procedure is quite simple. And in this video, we use the siesta calculation as an example. And for using one functions, it's a bit more complicated, and we will cover that in another video. Okay, thanks for watching, and see you next time.